In this ShowMe, we're going to revisit the cases of squares of binomials and products of sums and differences of the same terms by learning how to do their multiplications backwards. In other words, how to factor them. In this particular situation, pattern recognition becomes a bit of an issue. It's also important to remember a concept introduced recently in my previous ShowMes where you've got to divide out any common factors before you begin doing any more complicated factoring procedures. In any case, like the previous ShowMes, this is going to be heavy on examples, and in some cases there'll be more than one way to approach the problem, and I'll show more than one way. You choose the way that works best for you. I do think that the pattern recognition idea is an important one. I think that it's a good idea to learn to recognize these patterns. It's not always necessary to recognize them. In the case of the a squared minus b squared pattern, it's much easier to recognize the pattern. In the case of the square patterns, it's not absolutely necessary, but you'll recognize at the end of a problem, when you realize that you're dealing with a square of a binomial, you're going to feel a little bit silly about all the work it takes to factor things, when you could have just recognized the pattern in the first place. I'll show you what I mean. So here's a quadratic trinomial. It happens to be of the type where the leading coefficient is 1, so we can use the methodology from that ShowMe here to factor this. In that ShowMe, we asked ourselves a question: what numbers would multiply to 25 and add up to 10? And those two numbers would be 5 and 5. Following the methodology that we used there, we would rewrite this as x squared plus 5x plus 5x plus 25. Nothing wrong with doing that. We're not wrong. We're going to get the right answer. The next step, take the first two terms and factor x. You're left with x plus 5. Take the last two terms and factor 5, because that's the GCF. You're left with x plus 5. Well, the two terms have x plus 5 in common, and x plus 5 happens to be what's left over, which means we're not quite done. The simplest way to write this is to write the quantity x plus 5 squared. Now that we're there, it seems a little bit silly that we went through all that. Here's why. This polynomial is in a form that should be familiar to us from a previous section that we did. The pattern that we're looking for is this one. And it exists here. It exists because we can treat x as though it's a and 5 as though it's b. You write this that way then. You have x squared plus 2 times x times 5 plus 5 squared. And it works. That's the same thing. Now, why do we care about this pattern? Well, we learned earlier that this pattern is equal to the quantity a plus b squared. Well, that means that our polynomial is equal to x plus 5 squared. So if we were tuned in to this pattern, if we were watching out for it, it would be a very simple matter to go directly from what we're given here to where we ended up. And that would be the goal. It would be nice if that were automatic. It's much faster than doing all this, for instance. In any case, if you do it this way or in another way that you found reliable, that's fine. At the end, you're going to have two factors like this, and you need to make sure you rewrite them in the simplest form possible. I like pattern recognition. I think it's an important skill for anybody who's serious about their math. So I recommend that you develop that skill and practice it. Here we have another quadratic trinomial. The first leading coefficient is 1. But before we go any further, let's investigate. Does this fit the pattern that we learned earlier for squares of binomials? Well, if that were the case, you could take half of this number and square it, and it would be equal to this. Here's what I mean. The pattern we're watching out for is a squared. In this case, it would be minus 2ab plus b squared. Well, a is 1, so it really doesn't have much to do with anything in this particular problem. b, if this were a square polynomial, b would have to be 11, because it'd have to be half of this number, because that number also includes a 2. Well, if b were 11, what's the square of 11? It's 121. Now we're on to something. Now we know that b is 11, and this is a square. So, whenever you're looking for this pattern, if the leading coefficient happens to be 1, just quickly take half of the middle number and square it. If it happens to be equal to the number at the end, then you've got a square of a binomial, and this is going to be a very easy factoring task. It's a really good idea to memorize the square numbers up to a certain point. I've memorized them to 30, and I've memorized the pattern after that, so that I can quickly generate square numbers in my head. Now, I'm a bit of a nerd about that sort of thing, but it really has served me well, not only as a student, but whenever I've actually had to use the numbers, and I practice using them. I don't work out in the quote-unquote real world anymore, although I did do that for a while. But it's still important to me to be able to do calculations quickly in my head, so that when I give my students examples or when I give them help, we can quickly get where they're having trouble going. So this is a useful skill to develop, and depending on what you do, it may be a vital skill for you. In any case, if that first number is 1, take half of your middle coefficient, square it. If it happens to match the final number, you're onto something. You've got a square binomial. Well, how does this factor? Given that we found it fits the pattern, it's x minus 11 squared. Without all the talking that I've done, that would have been a very quick factor. And we're going to go a little faster now that I've said all I need to say. So, how do we check this when that first number isn't 1? Well, you're looking for square numbers. Are your leading and trailing coefficients square? If they are, you might have something. Well, 9 is square, 4 is square. All right, what are their square roots? The square root of 9 is 3. The square root of 4 is 2. Remember, this middle term is negative 2ab if we have a square situation. Well, 3 is a, 2 is b. What is negative 2 times 3 times 2? It's negative 12. It matches this. We have a square trinomial here. Well, it's going to be a pretty easy factor then. It's going to be 3x minus 2 squared. Now, how did I get that? Well, this first term has to be, well, the whole pattern is a squared minus 2ab plus b squared. So this first term has to be a square of whatever goes right here. Well, what's the square root of 9x squared? We already know the square root of 9 is 3. The square root of x squared is x. So take 3 and x and put them together. Can you get 9x squared out of that? You certainly can. In the same way we knew 2 was going to work, because 2 squared is 4. So this is the way we factor that. And if you're good at pattern recognition, just remember this rule. If these leading and trailing numbers are squares, you need to run the check that I just demonstrated. And if it works out, you're done. A lot faster and with a lot less work than if you don't catch it. Now, just to make the point that this works, I'm going to do this again using the method I've already shown, so that you can see that if you don't spot what I'm talking about, you can still get the right answer by sticking to the method I've taught you. Let's say we don't spot it. Okay, take 9 and 4, multiply them together. You get 36. B is negative 12. You need two numbers that have a product of 36 and a sum of negative 12. What would those be? Well, 36 has a fair number of factors. You got 1 and 36, 2 and 18, 3 and 12, 4 and 9, 6 and 6. I like 6 and 6. So we'll break up negative 12x into negative 6 and negative 6. So we'll have 9x squared minus 6x minus 6x plus 4. The first two terms factor. They have a GCF of 3x. 9x squared divided by 3x is 3x. Negative 6x divided by 3x is negative 2. We have a negative here, so we're going to have a negative here. What do 6 and 4 have in common? I think that would be 2. Negative 6x divided by negative 2 is positive 3x. 4 divided by negative 2 is negative 2. And now we start to feel a little bit sheepish as we write out 3x minus 2 times 3x minus 2, and that is the quantity 3x minus 2 squared. Now, don't feel too sheepish. You got the right answer, and that was the most important thing you were supposed to do. However, in the future, you might want to work on your pattern recognition. Pattern recognition is a crucial skill, not just because it makes some problems go by faster and eliminates some chances to make mistakes. Sometimes pattern recognition is the only skill that saves you when you get yourself into a complicated problem. Okay, now that we've dealt with squares, let's talk about the product of a sum and a difference of the same two numbers. Earlier in our sequence of ShowMe's, we learned that you produce a difference of squares whenever you multiply a sum and a difference of the same two numbers. This is a difference of squares. X squared is obviously a square number, and we know that 49 is 7 squared. So this is x squared minus 7 squared. Now, if we're going to use the pattern, the answer is x plus 7 times x minus 7. I can't think of a better way to go. It's that fast, it's that easy, and it's a very easy pattern to recognize as long as you're familiar with your square numbers. But let's say that you're just not. Let's say that you just don't know your square numbers. Hard to believe you wouldn't know that 49 is 7 times 7, but if that were to happen, how do you proceed? Well, you don't have a middle number here, but all the factoring that we've done depends on having a middle number. Let's have a middle number. If there's nothing there, and you're adding things, which in polynomials, these are sums of terms, that middle number has to be 0. But our middle terms have to have x's. Okay, have an x. It's not going to change anything, because 0 times x is still 0. So, we have to ask ourselves, what two numbers would produce a product of negative 49 and a sum of 0? Well, 49 has only two pairs of factors. You got 1 and 49, you have 7 and 7. Now, because we're looking for a negative 49, the two factors have to have opposite signs. And if they're opposite numbers that add up to 0, then they're going to be negative 7 and positive 7. So, we're going to break 0 up into 7x minus 7x and minus 49. The first two terms have x in common, so you have x plus 7. We have a negative here, so we're going to have a negative here. 7 and 49 have 7 in common. Negative 7x divided by negative 7 is x. Negative 49 divided by negative 7 is positive 7. Well, we have x plus 7 in common, and x minus 7 is what's left. So you can still get there. It's a bit more work. I don't think you need to go here at all. I think that you should be able to go from x squared minus 49 straight to x plus 7 times x minus 7. And I'm not going to model doing all this work again. It actually confuses the problem far more than is necessary. Our last example has a reminder about an important idea that we introduced in a previous ShowMe, and that is that the first thing you should always do whenever you're factoring anything is look for a greatest common factor. Factor that out first. It's going to make life easier because the numbers you're dealing with will be smaller, have less factor pairs to sort through as you're doing your work. So, do these two terms have any common factors? Yes, they do. They're both even, so they both have 2 as factors. 8x squared divided by 2 is 4x squared, and negative 50 divided by 2 is negative 25. Now I'm sensing that there are some square numbers in the vicinity. I think that 4x squared is a square. I think it's 2x squared. And I know that 25 is square. That's 5 squared. So that's going to be a difference of squares. That's going to be a sum and a difference of those two terms. It's going to be 2 times 2x plus 5 times 2x minus 5. And we're done. This pattern, this difference of squares pattern, always produces a factorization like that. The other risk to watch out for, as before, is once you've factored this 2, don't forget to keep writing it. If it's not there in your answer, you're wrong, and you don't have the right to be wrong. I hope that's helped. These two patterns are very common, and you can factor them, as I've shown you. You can factor them using the techniques I've demonstrated in other ShowMes. But I don't know why you would do that to yourself. It's far faster, it's far more efficient, it's far more effective, and down the road it will be very useful to have good pattern recognition skills. Cultivate that skill. Get used to looking for patterns. It's not a hard process at all to spot the square numbers that give you hints as to where you might go with your factoring patterns. Of course, if you don't spot it, you can still get there, and you still should, using the techniques I've taught you. They just take a little bit longer. They take a few more steps and more writing, and because of that, they give you more chances to make mistakes. And that's why the fastest way to get to the right answer that follows the rules is the best way to go whenever you can.